The distance between two objects also dramatically affects the gravity or the force of gravity between them. And that is governed by something we call the inverse square law. If we think about taking a number and taking the inverse square of it, let's say, for example, the number 5. If I want to take the inverse square of 5, first of all, the inverse of 5 is 1/5. The square of it is just putting it to the second power. So the inverse square of the number 5 is actually 1/25. If I wanted to take the inverse square of, let's say, 1/2, okay? If I take the inverse of 1/2, that's 2. And if I square it, it's to the second power. So the inverse square of the number 1/2 is actually 4. So when we talk about the inverse square law, let's keep that math in mind. So here we look into distance and gravity. The closer the two objects are to each other, the greater the force of gravity is between them. The further away from each other they are, the weaker the force of gravity is. So if we look at this example right here, if the distance between two masses is now triple the distance, so that's 3 times the distance, then the force of gravity between them is now 1/9 of what it used to be. How did we figure that out? It's from the inverse square law. If you do 3 times the distance of what it used to be, the inverse of 3 is 1/3. If I square it, it then becomes 1/9. So originally, the force of gravity between the two objects was a certain amount. But now that you've tripled the distance between them, you've cut the gravity's force down to 1/9 of what it used to be. And it all has to do with this inverse square law. If we look at the examples here on the side, between two masses is a certain force of gravity. So that is our starting point. Now, if I double the distance between these two masses, I now end up with 1/4 of the gravity I used to have. Why? Because of the inverse square law. If I doubled the distance, the inverse of 2, which is double, is 1/2. And if I square that 1/2, it now becomes 1/4. So due to the inverse square law, since the distance is twice as large, I now have 1/4 of the force of gravity I used to have. If we look at these two objects, the masses are still the same as they originally were, but now the distance is 1/2 of what originally was. Well, if I take the inverse square of 1/2, 1/2 inverted is 2, and if I square that, it becomes 4. That means that by cutting my distance in half between the two objects, the force of gravity is now 4 times greater. Does that make sense? I'm hoping so. It's all about the math. The closer you get, the smaller the distance is between you, and the larger the force of gravity is between them. And to try the last one out, take a look at this. Not only did I double the distance, but I doubled both of the masses. So let's look at the masses first. We know that if the mass is now 4 times greater, that means our gravity is 4 times greater, right? Because double mass means quadruple the mass total. And besides that, we also doubled the distance. So the distance was doubled, but when we look at distance, since it's further away, gravity is going to go down. So doubling the distance really sets it as, well, let's do the inverse square law here. 1/2 is the inverse of 2, and squared is 1/4. All right? So now, because of the masses, gravity is 4 times greater. But because of the distances, the force of gravity is 1/4 of what it used to be. So if we take those, 4 times greater times 1/4, what do we end up getting? Yeah, they cancel out. So the force of gravity stays the same. So by quadrupling the mass and doubling the distance, the force of gravity between the two objects evens out and stays the same. But how would you do that unless you understood that for distance we follow the inverse square law, and for mass we know it's directly proportional? What if the distance between the Earth and the Moon was doubled? Well, that would mean that the force of gravity would be reduced to 1/4 of what it used to be. How do we know that? Because of the inverse square law. When we're dealing with distance, doubled means 2. What's the inverse of 2? 1/2, and you square it, and you end up getting 1/4 for your answer. What happens if we tripled the distance between the Earth and the Moon? Well, you'd end up having only 1/9 the force of gravity between them. Why? Because if you triple the distance, 3 is inverted to 1/3, and you square it, you now have only 1/9 left of what you used to have. Now, if you take the distance between the Earth and the Moon and cut it in half, so the distance is half, which means when we deal with distance, we invert it, which is 2. 2 squared means 4. That means that because of the distance cut in half, you have 4 times greater the amount of gravity. But it also says, what if we increased the Earth's mass by 2? So we double the Earth's mass. Well, if you double the Earth's mass, you are going to have 2 times greater the amount of mass, but that means that your force of gravity is going to be 2 times greater. So you now have 4 times greater the force of gravity because of the distance being reduced, but you also have 2 times greater the gravity because of the mass being doubled. So overall, 4 times and 2 times greater, 4 times 2, means that there is 8 times greater the amount of force of gravity. So they can work together, they can work against each other, but they both play integral roles. So if we go back to thinking about the sun pulling on the Earth, yeah, the sun is humongous. So the Earth wants to orbit around the sun due to gravitational force or pull. But the moon, even though it's affected by the sun, still orbits around the Earth, even though the Earth is so much smaller than the sun, because the moon is so much closer to the Earth. So distance and mass both play a huge role in gravity. Remember that. To end with this graphic, the acceleration of gravity changes as you get further away from the center of the Earth. We know if we are basically on the surface of the Earth, the acceleration of gravity is about 9.8 meters per second squared. But the further away we get from the Earth's center, the acceleration of gravity actually drops to the point where eventually you're out of the gravitational pull of Earth so much that you barely accelerate towards it. And that's why it has this decaying model, because it never really reaches 0, but it gets less and less and less. So the Earth's always going to pull on us a little bit, but it's going to be so small and so tiny by the time we get so far away that we aren't going to be affected by it. Something cool to think about, but that at least starts the beginning conversation on gravity. I hope you understand. Feel free to jump back and forth through the video to get any extra ideas, and check online as well. I have linked some extra videos that might help you better understand gravity as well. Have a great one. Thanks for listening.